willing to show to produce the content. So it's a bit the same. But if you look at television, for our company, the real breakthrough was in the World Exhibition of '58. So televisions really took off then. But from that point onwards, we already see the first seeds of what our company is going to do for the next 50 years. We see from the 60s onwards that the company will start focusing on industry. And also, and I didn't mention this already, the Barco television sets at that point were one of the only television sets supporting all the multiple standards. So we had PAL, the French used CCAM, the Americans NTSC, and those television sets were multi-standard. And basically we went along down to in the 20th century until we have to, if we look at the start of the new millennium, what is our company doing? What's the technological environment? First of all, we see that the technologies that are being used for projection, for optics, last relatively long. So you have a long period in which your company can invest and create and generate expertise. The changes in the technology are non-disruptive. This means not only do you have a long time to create the expertise within the company, changes to the technology happen slowly and typically build up on previous expertise. We also had a very big competence center in optics. So people doing opticians making lenses for projectors, cinema projectors, were really at the core of our design. And at that point in time, we had a full chain development. Not only did we make the PCBs, we equipped the PCBs, we made the design of the hardware, but also we made ASICs, with the exception of CRT. So, where were we at the turn of the century? At the turn of the century, our designs were really hardware-centric. Okay. At the core of a PCB, we had an FPGA. And the pun goes, the FPGA, the rest is peripherals. So from the moment you have the PCB was made, the biggest decision to make what FPGA we're going to put on the PCB. We see a rise of the DSP solutions. Already there's a little bit more software. The need for flexibility, multiple codecs is rising, and then we have some DSP there. And the processor that's on the board, or may not be on the board, is basically only for controlling stuff. So simple APIs, loading the DSP cores, keeping everything in touch and giving feedback. Where do we see software in our systems? It's based on the network. So on the network, if we focus that most of our systems have been designed to provide dense solutions, we have boxes of 10, 20 PCBs, each controlling a number of streams. As a customer, you don't want to configure each and every stream on each and every board in each and every box. So we have software only for controlling the overall system. So what changed? I mean, I think I mentioned some of things already. The development was pretty long. So if you look at a typical design in the early 2000s, resources were committed for 4 to 5 years. It's a very long time to predict technologies, to predict market environments. Development was also often done to keep on producing and improving in the field. So we ship stuff to the customers that has a basic functionality, and afterwards we're going to, based on the feedback, based on the environment, improve the existing software. At that point, we were confronted with a very long component lifetime. All the systems that we were selling had to be supported for 10, 15 years. The problem then is that we immediately, for a component selection, entered the industrial range of components. The industrial range of components is not only expensive, but from the year 2000 onwards, we see that they're really underperforming with respect to the consumer side. And we see that the technology is no longer driven by the industry, where in the past you had the opportunity and the area to really have an expensive system driven by industry, and then you made derivatives for consumer market. Now we see the opposite. We saw that the consumer systems, with very short lifetimes, like 18 months, 24 months, is technologically much better than what we see in the industry systems, the industry components. And from that point onwards, I think what basically shattered everything was the rise of mobile. If you look at mobile, why is this so important for system design, and certainly for us? Well, if you look at research before the year 2000, it was basically aimed at power efficiency. You have the triangle: power, memory bandwidth, and speed. So there's a lot of research dedicated on how can I make my compiler do better loop transformations, how can I limit the transfers from external memory to internal memory, and such improve the power dissipation and the memory and the speed. This research obviously was driven from embedded systems. And I always pick out Android as a typical example of how completely this changed everything. We see embedded systems, handhelds, running Java with automatic memory management. So by nature, these things are no longer efficient memory-wise. So every research that has been done over the last 10 years with respect to handhelds and efficiency is contradicted with something that's being pushed in the market with very big numbers. And the solution, as it has been a couple times before, was not to improve the technology itself or to improve the code or whatever. It was to add more resources to a system. So we see, instead of having handhelds with very efficient code base, with a very power efficient processor, now we see that they're adding more cores, more speed, and battery, and more heavy battery. We see that instead of processors that are running at 100, 120, 300 megahertz, no over 1 gigahertz and multiple cores is getting the norm. In the past, in the early designs in the year 2000 and in the beginning of the year 2000, if you could make a design with a CPU that was $2 cheaper and run at half the speed, you were the best man in the company. You made it efficient. Now we see that this is completely the opposite. And from a hardware point of view, it's getting very similar to general purpose. So what is the difference between a general purpose processor and an embedded processor? So it's also from a software point of view. I'm going to use, well, after this introduction, GStreamer as an example of how this rippled through the company. We were using GStreamer as a driving force to make this change happen towards a more software team. So if you look in 2006, we had the first try with GStreamer. At that point, we were making a successor to a streaming video solution. And we were not going to reinvent the wheel again, so we were going to use GStreamer. And we were doing this on a Freescale 8390 49 core. Okay? And we did some tests. We used basically our same system as we did in our previous system, software-wise, but changed the software to GStreamer instead of a custom stack. So what problems did we have? Well, first of all, we were using UClipC instead of glibc. At that point in time, the overhead for switching threads was terrible. So you're running the same software on a 300 megahertz glibc-based system and this UClipC system basically halved or one-third, made you run it at one-third of the speed in comparison of the two. Of course, cost at that point of the design was driven by the hardware. That means at the point that we were testing the software, the hardware was there. This is a typical example. Hardware engineers make a board, this is the board, now write software for it. So we didn't have the opportunity to change the library anymore to something, to glibc. We didn't have the footprint, we couldn't put glibc in there, it was just too big. And of course, we were comparing it with our previous stack. Our previous stack was custom written in purely in C, and had a limited support of protocols. So our handling of RTP was just drop 16 bytes. If you compare it then with GStreamer, that actually does calculations and tries to compensate for the jitter, you're never going to win. So yeah, this continued. And we decided to go for yet another custom stack. We knew that our previous stack wasn't good, but we're going to write another one because, well, we couldn't use GStreamer. But some things, well, they really stuck a little bit. We kept some kind of modular design from GStreamer. We saw that the monolithic solution, where we basically have one while loop or a couple of while loops in a single thread, was, well, not the best way to go. And yeah. There were a number of things that, well, we couldn't use GStreamer at that point in time, but it was getting to the engineers pretty obvious that, well, it's a promising technology. So when the opportunity presented itself to make a server-based system, we went back to using GStreamer. Of course, at that point in time, using a server-based system, basically all the limitations that we had previously were gone. Okay? It was for us the perfect opportunity to build up expertise without running into any limitations. We had a very small team working on that, 2-3 persons initially. The modularity allowed us not only to support a wide range of encoder cameras, we also started working with upstream, basically submitting our patches, getting reviews of them, and some patches like, okay, we've done this, hey, have you considered this use case? So it became pretty obvious that this was the way to go. And finally, this also got rippled through to other layers in Barcode managers. We saw that the stability, the ease to change pipelines, to change behavior, to switch sources, what was really being seen. If there was a need for a new camera, typically, well, they could have it in a relatively short time span as compared to previously. Previously, with our custom stack, it took engineers quite some time to hopefully just make the fix in the stack. And if it was not good, if they needed more work, it took them weeks or months to do so. Now we could have the same thing a couple of days or a couple of weeks, because most of the problems that we encountered with cameras, network streams, they were either smaller problems that the camera did, or smaller bugs on the GStreamer side. Makes it completely different with respect to writing everything anew again. From that point onwards, we also see that gradually the custom stacks are being replaced with GStreamer. So we have our existing systems and parts of the front end where there were custom stacks are being replaced with GStreamer. We see that network streams, compatibility issues are no longer always solved on the devices themselves, but they're solved in the network. So if you have a new camera that behaves oddly, we solve it in GStreamer and put out a standardized stream on the network. Also, yeah, as a company that does visualization, we have our fair share of custom codecs. So it also makes it pretty easy, GStreamer, to integrate those in all kinds of solutions. And what's really driving there is that we have an external API. I don't know in your company how many meetings you've spent on APIs before you could start writing code. Everybody has his opinion, but having an external API basically short circuits the entire discussion. This is the API, you abide by the API, and if your code follows the API, it's going to work and integrate it into the framework. If we look now, we have a stack that has proven its use on x86, but it's running almost completely in user land. Okay? We've seen our number of presentations about embedded systems and system on chips, but in general, the bulk of the software, the streaming software, is running in user land. If we look to the devices, if I think back to something like 2008, 2009, at that point in time, in Debian, the third most popular architecture was ARM. And this was almost exclusively to the rise of a very cheap ARM-based system, the NSLU2. We see that people are picking up software writing on all kinds of devices, and everybody notices as well, once you're in user land, there's basically no difference running on 86 or on ARM or on PowerPC. So we can reuse the entire stack on any system. So once written, used everywhere. We can now, by using GStreamer, we can reuse our camera compatibility, our session management work, whatever that we've done before on an x86 system, we just carry it along to ARM or other systems. Obviously, when going back to an embedded stack, we are confronted with really dedicated solutions. The systems are written for a particular task and a particular environment. And the question often is, can we still use GStreamer for very high bandwidths, for very high quality? So one of the systems that we've been developing is just raw video at 60 frames per second in resolutions higher than HD. So obviously, if you look at an ARM core of 1 gigahertz, there's very little chance that you will be able to handle those amounts of data in user space. So obviously, well, we're going for a hardware solution. But if it's in hardware, what does GStreamer do there? We're not handling the software anymore. If it's raw video, probably we're not even going to have a decent session management. At this point, for this particular solution, we're using GStreamer simply for the caps negotiation. Okay. We have a number of devices in hardware, in FPGA, that are isolated with the Video for Linux interface. And we use the negotiation between the Video for Linux sync and the Video for Linux source to set the parameters, to set the resolution. So you have some output to a screen, you get some input from a network, you have a scaler in between, and you negotiate the capabilities. From the moment you have a standardized and negotiated capabilities, you push it to the hardware and you steer your FPGA scaler. The data handling obviously is, as is the network stack, is in this solution obviously fully in hardware. I think GStreamer also gave us an opportunity to obfuscate or to make the distinction between raw, which is very dedicated, you cannot handle it in user space, and compressed. Basically for GStreamer, for a modular system in general, there is no difference between the two. You just have data passing from one module to another module. So with the system on chips that we're using that have hardware support for creating H.264, we just need to reroute the data a little bit, steer the data a little bit, and we have a completely different solution. If it is network to network, network to video, or capturing to network, there really is not that much difference. We also use, if you if you're creating a custom hardware solution or a GStreamer based solution, there are a number of ways you can go. We've seen a number of modules in general that are custom written for a particular chipset. So you have a particular chipset and the vendor enters with a module that only steers that chipset. In our solution, we've decided to basically contain the hardware as close as possible to the hardware. Which means that we were not really interested in carrying all these exotic chips, all these exotic systems into user space. We just wanted to keep them in the hardware. So we decided to hide the hardware between simple video for Linux interfaces. So there is no rippling through of custom modules into user space. Also, because, and there's another consequence of this, because it's in a video for Linux interface, again, there is no difference between raw and compressed. If you have a capture device that does H.264, or you have a raw device that does H.264, and both have a video for Linux interface, it's the same for userland. And yeah, I'm not going to go into detail on the OMX framework, but that's a good thing to keep that chilled up. Obviously, in our company, we've had our fair share of discussions. The switch to GStreamer really didn't come that easy. And a number of remarks that you heard were, well, first of all, GStreamer is slow. We can't use it. GStreamer adds a lot of overhead. We can do it better, we can do it more efficiently. And if you take a step back and look from where these remarks are coming, simply from people that have a very long history in hardware. They've entered the company 10 years ago, 15 years ago, have a large expertise in doing hardware, VHDL, and in writing while loops. So they want to keep on doing that. But I think we've started to prove the opposite over the last years. Well, I think we need to admit that GStreamer can be slow. But from every point that we've seen that GStreamer is slow, it's really not because of the framework, it's because either there is a bug in GStreamer or a driver, or we see that our hardware is spitting out some kind of format that's not exactly handled yet. For good reasons, by the way. So, just fix the problem. So in the case of ALSA, one thing you see with system-on-chip systems is that all the limitations or all the effects of hardware are blown up. If you have a very powerful x86 system and you do memory allocations, not in the power of 2, it's going to be hidden. If you do it on a system-on-chip system, where your hardware is much more constrained, such things are blown up and the effects are seen immediately. So it's just a matter of fixing it. Well, these are two smaller examples. And I think we need to convince people that basically a number of bugs in a framework or any software stack shouldn't really be an excuse for writing yet another custom streaming stack. Because even with the size of Barco, which is locally very big, but internationally really very small, I don't think we can actually spend the efforts of writing yet another stack that, by design, you know, is going to underperform to all the resources that are being poured into an open framework like GStreamer. What did make the use of GStreamer in Barco so different to the previous experiences we had with open source? There is another talk also about more embedded systems from somebody in Barco, but the largest project that we've been working with for some time on basically all our systems since the early 2000s was the Linux kernel. So the Linux kernel is, from a developer point of view and from a system design point of view, very different. The kernel itself is really tied to the hardware. If you make a board and you make and you put an FPGA next to it, your design and your hardware is really going to be tweaked to that FPGA tweaked to that board in a large extent. So the reuse of the custom reuse is rather limited. In contrast, if you put it in user space in a framework like GStreamer, you write it once and it can be used everywhere. So no longer do you write solutions for one board, for one system. You write them once and you just can carry them along in other systems. We're now considering to add support for, we make a system with a certain goal. The added price or the added developer cost for example, adding preemptively a custom codec in that system is very low. It's just an extra library we need to add. So we see that by using this, those things are in the company easier integrated. A little bit tied with the API discussion is that we had a lot of meetings about tooling. There is always some commercial company that convinces somebody that they have really the best tool to do the task. And you end up in long meetings with basically a very old system that has a fancy front end to it, and if you're not careful, you get that split into your stomach and you can use it for the next so many years. This is pure theoretical, of course. We never had that. If we look on how tooling is now being handled as a result of open source development, and in particular GStreamer, is that no longer, well, it depends. The developers don't think that they have to modify the way GStreamer is working because it doesn't fit our internal policies. So, for example, if GStreamer comes in some kind of repository format, developers really aren't going to question that anymore. They're not going to make snapshots and put it into another repository just because the company guidelines use that. We see that this particular example about the repository actually is pushing changes within the company. We are no longer determining how people would work from the internal point of view. We are integrating external workflows into the company. And this is driven by developers. Okay, well, we are still a company. This means we have a lot of people that meet other salespeople. So, but instead of having complete new systems that really are not used by anybody else but in a corporate environment, we now see that those discussions are typically limited to the sugarcoating on top of that. For example, in the case of Git, there are discussions going on about using some commercial tool for giving it a web interface, but from a developer point of view, we don't care anymore. If we look at all the changes from a technical point of view, I think we've had most of them already. But it also has a human factor. If you have a company like Barco that has been dedicated and specialized in hardware design, and for all of a sudden, in a relatively short span of time, you need to switch to new technologies, a new way of working, you need to migrate the software. So, I think some people in the room can vouch for that. We're adding a lot of training. So training really is the key. Why is training so important and why is a framework so important? We can now easily integrate external people and give training about the framework without them to need the full internals of our software. It is an external system. It has a clear API. Everybody's using it. We're in the process of migrating a lot of hardware engineers to software from the bottom up. So typically, where you would have kernel developers, we're moving them one step upwards. If you had low-level user software developers, we're trying to move them slowly into GStreamer. The FPGA people, certainly the younger ones, are being moved slowly into software. So, and that way, in combination with training to ease the access in hardware, and reuse the resources in software. Custom hardware design really does add a big threshold for competitors. Okay. If you would need to make a custom hardware design, it's tens of thousands of euros, hundreds of thousands of euros to make your own PCB, to make your own development. This has changed with software. Software, anyone with a laptop or even a student can start writing code. And yeah, I think like in any company, I haven't met anyone that didn't have the discussion, is that, well, we shouldn't use GPL. Because if we use GPL, we have to give our code away. We shouldn't use LGPL. Same thing. And in general, well, we've actually, well, luckily, quite some time ago, there was even an official ban for using open source software in Barco. But I wouldn't be here. We've passed that since quite some time. Currently, we're focusing on cooperation, not only within the company on using the same framework, but also externally. We really have to ask ourselves, is our added value really in supporting that exotic camera? Do we really need to keep this internal or just push it external? And also, yeah, and that's a discussion that's going on and will keep on going on. Some time left. Our use case is special. All those other guys out there, they don't know what we're doing. We're going to write it because we know better, and our use case is really completely different. We see that we need to step away from that. The newer designs are really no longer limiting themselves with that. And of course, instead of trying to protect your development, I think it's key to keep on moving, to be just one step ahead, to go to that next challenge. If I look at the new systems that are currently in the pipeline, I think it's for the streaming solutions, probably not really the first time, but it's really getting through that no longer is the situation there where you have a board that comes to the software department, now write software for it. We see that the design of the software, the design of the overall system is being governed by software. It has a functionality. The functionality entails a number of technologies, of which GStreamer is one of them, and based on that technology, the hardware is being designed to fit into that overall view. Where interdivisional meetings were in the past basically limited of, you have our board, make it work in your system, and you have our board, fix it in your system. We now see that these meetings are happening before the design. So people are thinking on what will be the challenge that we have, what's the software going to use, how are we going to structure the software to best fulfill the requirements. And also, because we're starting to use more and more the same technology, we have more peer review. We're getting people with fresh pairs of eyes, not limited in all our use cases or skilled in all the design, to have a look, hey, what you're doing there is not quite correct. Basically the same thing as providing your patches upstream. And GStreamer, obviously, I've mentioned a couple of times, is key there because it has stable APIs. You can develop independently. When submitting to Bugzilla, you really have good peer review. Within the company, it's becoming a common reference. And also, no longer do you have a number of company-schooled experts that are always the bottleneck, but now if there's really a bottleneck in the product design, it's very easy to get external people, like consultants, to fill that gap, that temporary gap. And like I mentioned before, training really is the key. Not only because we're having the transition from hardware to software, but also if you pull in external experts, they typically have another view, have knowledge that is not contained within the company. So they have a fresh pair of eyes, a new perspective into things. So really see another value there. For our system design, I think it's getting through that the key is for adding value to the system. Okay? So we have a network-based system. What can we do to improve the system? What's new to it? And writing yet another network stack obviously isn't one of those things. We are no longer reinventing what's already there. Yeah. Are there any questions? Nope. That's right.
So there was a talk earlier about zero copy I/O going, you know, using V4L device drivers, a whole bunch of zero copy I/O stuff. I was wondering if you guys have had to make a lot of changes, you know, maybe in patches that haven't been upstreamed to make that work with your hardware.
Now, for that particular case, no. We're using some kind of zero copy, but there's a lot of kernel work involved for basically isolating OMX. But we haven't submitted that particular kernel work for a number of reasons. First of all, it's a TI chipset that uses a really old kernel. So we would need to be submitting to 2.6.36 or 37. Secondly, that chipset is on the way out. So I don't think people are going to use that, and that's why that's limited. On a user level, so everything that's GStreamer related, everything that's being done on module level is being submitted upstream. There are a number of developers, if you know their name, that you can find in Mozilla. Typically our changes are, well, used to be in third-party camera support, but also now as a result of doing, again, embedded work on a system on chip, we have some fixes on ALSA, for example, and H.264. But the zero copy, no, that work we are not involved with, and it's completely next to what we're doing, unfortunately. It's not a chipset also. It's again, I mentioned it also with Linux. The lower you go to the hardware, the more specific it becomes to your particular use case. Unfortunately. No.
Any more questions?
But if anyone would be interested, I'm sure we would welcome peer review on the work. But nope. Okay. Thank you.